Alright, hell yeah. So we have statics, and this is Hibbeler. Now this PDF that you can find online, so this is pretty sweet. We have a problem. What we're going to go over is free body diagrams, and kind of the gist is I want to be able to, cut out one of these masses. So that's what we're going to do. We're going to actually cut out this. It's called a roller, and then apply the forces to it, and then see how the free body diagram works out. Now this is a rolamite. In the description I'm going to put a video to someone who makes one of these out of Legos. These are two rolling like drums or rollers, so they do have axles, and they're able to spin freely. Now you do have this ribbon that winds through them, so these are able to roll back and forth. And if you connect one of them to a motor, in the video that is in the description, it's pretty cool. A guy makes one of these out of Legos. It's probably one of the best visuals of what a rolamite is and how it could be useful. Anyway, excuse me. So with free body diagrams, we have this idea in statics that this thing is not moving. You know what I mean? So this is a statics book. So everything in this book is stuff that's not moving, or you get to a point where like maybe it's starting to move. But in this problem, we just have this ribbon that is tensioned. You know what I mean? You could imagine that. We're going to apply some tension. It's going to hold these rollers together. There's nothing else that's actually holding this, system together except a ribbon that goes around these rollers. And then we apply 50 Newton force. And when we do that, we kind of wedge these rollers. Kind of want to pass each other with that tension. And then what we do is we kind of wedge. And with these plates being rigid, we end up getting a normal force, kind of that when we do wedge these, we do see these normal forces. And so this problem is actually pretty basic. It's one of those where you actually don't want to just chop out an individual disc. So let's do it like it should be done, where you want to chop out the whole, like everything in blue. So we're going to take both those rollers, and then we're just going to apply. And how I like to do free body diagrams is, anytime I'm going to chop out something, I pretend like it's in outer space, just floating there with no forces. You don't have any gravitational forces around. And then I go back to kind of Earth, and then see what forces are known. You know what I mean? Because if I'm applying a 15 Newton force, maybe I have a gauge, a spring gauge, where I actually know that I'm applying that force. So sweet. So I'm gonna put that on my drawing. Since that is a known force, I have 15 newtons there, and then 15 newtons here. Okay, so there's going to be 3 rules. Well, actually, just kind of 2. For statics problems, and we use the equation F equals ma. So I'm going to just draw a chunk of mass. Same thing. It's just floating in outer space, and its velocity is 0. But now I'm going to put a force on it. Let's say of 50 newtons. So in this case, this thing is going to be moving across the universe that way, and it's going to be increasing in speed, because I'm constantly applying a 15 Newton force. That's basically the principle of F equals ma. And then we can kind of set directions to this. We can set this as the x direction. And we can say forces in the x are mass times acceleration in the x. And in this case, we will have an acceleration because we identified a mass. We identified forces on it. Cool. Now, let's say I apply a 15 Newton force this way. Well, I identified a force over here, but I have to add up all the forces together, and you can see that these kind of balance. So cool, I have 2 forces that are equally pulling this mass. It's not going anywhere. I think that's very visual. So what we would say, and this goes back to like, hey, if this was something on Earth, maybe a chunk of mass with in between 2 different springs and a wall, we could visually see from this experiment that our velocity is 0. This thing's not moving, but we can still identify, maybe we have a spring gauge on these springs, and we've identified that we are pulling on a force. So we are pulling 15 newtons that way, 15 newtons that way, but we still observe zero velocity. So that's kind of the heart and soul of statics, is where you still have this F equals ma equation, but you have a 15 Newton force in the positive direction minus this 15 Newton force in the negative. Those are going to sum to 0, and what we say is that mass times acceleration, it does have mass, let's say it's a 1 kilogram mass, but the acceleration is also 0. That kind of satisfies this equation. So what you'll have in statics is forces in the x is equal to mass times acceleration in the x, where that is 0. So you just get forces in the x is 0, and this is the sum, adding up all those forces in that direction. Then you're going to get forces in the y, same thing, and you're going to sum the forces in the y is equal to 0. Now this is where I run into a hiccup, because I really want to explain if we do have a moment, because that's the third equation. And I'm just going to write sum of the moments are equal to 0. You know what I mean? I'm not going to go into an example. In another video I will, because I think there is a disconnect here where you're just like, I can visually see that if I put this force on here, that's going to travel that way. But then when I go over to this example, this is a moment. You know, we have kind of the center here, and this is a moment of a couple. I'm just going to say this is the distance d. And the moment on this, like the number for the moment, and the moment is going to be force times distance. So we identified a force and we identified a distance. And so this one's going to be 15d. That's going to be the quantity. And moment is a leverage. It's a force times a distance. Now, you might be familiar with just taking one at a time, and you would say this is d divided by 2. So we would have a moment. From this point, we have a moment of 7.5d, and then this one is 7.5d. Those are going to add to 15. That's why if you have this, two identical forces separated by a distance, this is called a couple. Now, it's still a moment. You know, you can still just sum them up as it is a force. This is a force times a distance, and this is a force times a distance. Using the right-hand rule, start from whatever point you're trying to take your moment. Put your fingers in the direction so you get perpendicular to that force, and then sweep your fingers in the direction. And that's going to be not only kind of the vector, because moment is a vector of r cross force, but for, you know, if you're just doing, for our purposes, we're just saying, hey, this force is going to turn this thing this way. Cool, and sure, it's a positive motion, positive moment, your thumb is up. Now, if I had a force the other way, like this way, then that would be a thumbs down. And that's what we're going to see with these normal forces. All right, hell yeah. So let's do it. So if we just had these 15 Newton forces on these two rollers, this thing would spin this way, and it would increase and that kind of gets into dynamics, which that's what I don't want to dive into. Other videos I do. I want to explain the whole picture, but we're just going to say the sum of the moments have to be 0, because we go back to Earth and we see that this thing is not rotating. So if we identify two forces that cause a rotation this way, we need to identify forces that cause rotation the other direction. And so we see that those are going to be this normal force there and this normal force here. And then their distance apart is just like, hey, let's say it's just d prime or whatever. And so the driving force of this positive moment, and we can just go to our picture, is going to be 15 times this radius, and then whatever the distance is between these two. And we have a 30-degree angle, and it's kind of cool because a 30-degree angle, this is my radius, and the vertical component is going to be half the radius. So this is 1/2 the radius. That means this is also a 30-degree angle. This is also half the radius. So we have, for this problem, the moment generated by these 15 newtons is going to be 15 newtons, and then the distance is going to be 3 times the radius. So that's going to be 75 millimeters. And so we have 15 times 75, and we have 1,000 125 newtons, Newton millimeters. So that's kind of a force times a distance. That's the moment there. And that has to be balanced by these the normal forces causing it to spin the other direction. So we see that, you know, this force is going to be down this line, and this force is going to be down this line. So going from the center, we go towards the perpendicular direction of that force, and then sweep our fingers in the direction. So there you go. And then the distance between these, well, that's going to be cosine. This is r cosine 30, so that's going to be 0.866 times the radius, and we're going to have two of those. So we're going to have cosine 30 times 2 times the radius of 25. So we have 43.3 millimeters times the normal force has to equal this 1,125 Newton millimeters. And so we just take 1,125 divided by that answer, and we get the normal force has to be 25, and we're going to round 25. We actually, in the problem, they just round to 26.0 newtons. All right, hell yeah. And so for this one, this is 483, and we get a force of 26 newtons. All right, but let's do that one over again, just so we're kind of using all those equations, you know, like they're supposed to be. So we've identified a 15 Newton force here, a 15 Newton force here, and we have a normal force here and a normal force here. Okay, so let's use our equations. We're going to sum the forces in the x direction are 0. So we have 15 newtons minus 15 newtons is equal to 0. Cool. Now we're going to sum the forces in the y direction are equal to 0. We're going to have, this one's positive, so we have n minus n is equal to 0. Okay, so we kind of just have a check on reality when it comes to them. And then we have sum of the moments, and I'm just going to say about O, maybe the center of mass or whatever, is 0. And so, so that's where I identify, and let's just do them one at a time. So let's say I have this force of 15 newtons, so I'm going to write it in, 15 newtons, and the distance away from here is all the way up to there. So I'm just going to draw this little triangle in. I'm going to see that this is the radius. So it's this radius plus this is the angle 30, and this is r sine 30. So we're going to have 25 millimeters plus 25 sine 30, which this is just 0.5, and then we'll have 12.5. So 25 plus 12.5. So that's that one. And the direction of this is a positive direction. So sometimes just doing like a positive 1, that can really help you out, because then you can do like a negative 1 as well. So now we're going to add this. This force is going to cause a moment that way, and so the same thing. And instead of writing it again, I'm just going to say, whoa, I identified it's the same distance. I'm just going to do multiplied by 2 here. Okay, now I'm going to see that this. Now we're going to see how this normal force would rotate this thing the other direction. So that's going to be in the minus direction. So I guess I will just do a minus. That distance away is, we said this was 30, and we have r, this is the hypotenuse, so this horizontal distance is going to be r cosine 30. So we're going to have the normal force n times 25 millimeters cosine 30. Now cosine 30 is 0.866. And so sweet. So then we have to do the other one, and we see that's also a negative. It's going to be the same distance away, so we're going to have 2 of those. And sorry I didn't leave enough space here, but that full equation is equal to 0. So we sum the moments, just like we would sum the forces. This is a positive force, that's a negative force. So we've identified that this generates a positive moment, this one a positive moment, this one a negative moment, this one a negative moment. And summing those moments, those moments have values. It's the number is due to the leverage. The leverage is how much it would want to spin this thing. And so these two values have to equal 0. So we have a positive one and a negative one. And so, and then there's a couple of different ways to do this where you could just identify that, hey, this is generating a positive moment, and then the normal forces would generate a negative. So here, because this is minus, I can get it to the other side of the equation just by adding it to the other side. So the other way to do this is just set it up right off the bat. I'm going to have 15 newtons times this total distance. I'm just going to say the distance. If I do the distance, so instead of taking the individual force times, half the distance and then multiplying it by 2, you see how, hey, I took half the distance here, but then multiplied it by 2. So let's take the full distance and then just multiply it by 1. So we still take the 15 newtons. That's the definition of a couple, and that's kind of what's going on there. You take the full 15 newtons, and then you take this full distance. But you only do it one time. That's the thing that you can maybe get confused with couples. You're just like, you identify that these forces are equal, and that's the definition of a couple, where you have two equal forces separated by a distance. So you take one of those forces, 15, and then multiply it by the distance. That's 75 millimeters. Cool. And that's going to be a positive moment. And we're going to set that equal to the things that create a negative moment. And we see that these are going to be equal and opposite. The value on the normal forces are going to be the same. We've identified that they're generating a couple, that's wanting to spin this way, and the distance between them is 2 times the radius, 25 millimeters, and then cosine 30. Cool. And so, and then we have times that normal force. I guess I should just put that right out in front. So now we can solve for n. So n is going to be 15 times 75 divided by 225 cosine 30. And let's do that. So 15 times 75 divided by 2 divided by 25 divided by cosine 30. And so we get that 26 newtons. All right, hell yeah. So that's kind of how you do this problem. But now I want to go into what I want to teach, is how to break a problem apart, because that's going to give you... All right, hell yeah, switch batteries. But yeah, so doing it, cutting something apart is going to give you a better understanding of how free body diagrams work. All right, hell yeah. So where we're going to start is, honestly, sometimes the simplest stuff is like the hardest. So what I'm going to do is draw a rope. And we're still, like, maybe top down, it's going to be on a frictionless surface, or, or just horizontal, but we're going to put a spring right here. And then again, yeah, we're going to have a little device that's going to measure the tension. And then we're going to have a spring right here, a little device. And then so we're going to attach a rope to this. So here's the rope. And I'm just doing this to show you that, hey, this rope has tension. Okay, so we can kind of agree with that. And it's being pulled apart from both ends. It's kind of like the tug-of-war. And so the free body diagram says that we can, chop this. And I think this is a good method to visualize. Like, let's chop it and put it into outer space. So hell yeah. So there's our rope. And put it into, and again, we're talking about outer space where there's no, stars, there's no motion. It's like the only thing in the universe is just there. And we're going to go back and forth from Earth, or from the situation it's in, and then back to this. So, but yeah, that's why on this one, this is going to be a mass. Like, a lot of problems will be like, hey, this mass is negligible. Zero mass. Another way to look at that is just like, hey, this is a top down, like the earth isn't this way, but we're doing a bird's eye view, and maybe it's just resting on a table, and the table's made out of ice, so there's no friction or anything. Cool. So then what we do in a free body diagram is we say, well, is there any forces on this? And so that's why the first one to go to was like, well, does it have mass, and is there an earth underneath? And sure, we would have a gravitational force, but for this, we're going to neglect that. Cool, because it's going to be resting on an icy table. Who cares? But we do know that we've identified a force in both these springs, and so let's say it's just like our problem is 15 newtons. So we identified a 15 Newton force that way, and for every 4, I don't know, if you divide this by 4, you're going to get pounds. So I don't know, maybe it's like 3 to 4 pounds. Alright, so we're going to apply a 3 to 4 pound force on both sides. Okay, so, and then what we, and then we could have slowed down. We could have just read this one and said, whoa, we have a 15 Newton force. So just one at a time. Okay, so I have this mass. It's in outer space. I put a 15 Newton force that way. F equals ma says, well, this thing's going to be traveling across the universe that way. It's going to increase in speed. But we go back to Earth and we don't observe that. Okay, so we must go over here, walk over here, and this one must read 15. Because there's no other, we'll get that to in a second. So we have a 15 Newton force that way. Cool, now they're balanced, and we can just visually see this thing's not traveling this way or that way. Alright, and so, yeah, I'm trying to get like an order of operations of things you should be doing while doing free body diagrams. The other is to probably say, is there any other forces? And other places there could be forces is if something is touching this. And there's nothing touching it. We don't have anything. It's not, I mean, besides the support it's resting on. So, I mean, we should do that. Like, let's say, yeah, let's say let's say your table is right here. I think that would be a pretty decent visual. So we have a table, and now we're not looking at this top down. We're looking at it from the horizontal perspective. You do have an earth underneath. For sure, this thing does have mass, and you could divvy up you could chunk this up into, you know, every atom of this has a little component of mass. And due to the Earth being underneath it, there's a gravitational pull of that. And so, and you would have to add up all those little masses. And so, but just because it doesn't, as long as you put the mass at the center of mass, and the reason that you can get away with that is back to a problem like this. If I have like a rectangle, and then I should have drawn it the other way. If I have a rectangle of mass, and then if I put the force right in the center, this thing is not spinning. You know what I mean? So if I put the force of gravity right there, and then I put the normal force also through the center of mass, even though when this contacts the ground, there's going to be a force all over this thing. You know what I mean? You're going to have a tiny amount of force all over the table, but we can just put it, as long as we're going through the center of mass, that's kind of, that's one of the, and yeah, that could be kind of confusing, but that is one thing that we can do, and we do all the time in statics, just because, like, there's no way to actually represent. Well, I shouldn't say there's no way to represent, because you do smaller arrows, and then you do something like this. You have like the weight of this rope per unit foot. You know what I mean? So if this is 10 feet of rope, you're going to have the weight in newtons per, or like meter. Let's say newtons per meter. So that's going to be the weight of this thing, and that might be like a little w. And then you would have to multiply the little w by the length, and that's going to actually get the weight of the rope. So the force of gravity of that rope, because it has mass, that's going to be W. Cool. So now we're covering all our bases. We sum the forces. We're going to say this is the x direction, and then this is the y direction downwards. So, so the sum of the forces in the x direction are 0. So we have 15 newtons that way in the positive direction. And this is the negative direction, so we got minus 15 newtons. That's going to be equal to 0. Because our equation for this is forces in the x is equal to mass times acceleration in the x. And this is a sum of both these. So it's the sum of the forces in the x times the mass doesn't change, times the acceleration in the x. Cool. And then in the y, it's the same thing. We're going to have sum of the forces in the y. This is equal to 0 because by observation, this thing is not moving. It has 0 velocity downward or this direction. And so, so we would say this the normal force up is positive minus the weight down negative. That's going to equal 0. So from this equation, we would have the normal force is equal to the weight. And so we would have the normal force is equal to the mass of the rope times gravity. And I don't know, in my videos, anytime this mg comes up, I'm going to tell you where the force of gravity comes from. It's because this does have mass, and so here's you have this rope, and guess what? It's on top of a huge Earth that has a hell of a lot of mass. So this is the mass of the Earth, and this is the mass of the rope. And we have the distance between them is basically just the radius of the Earth. It doesn't really matter if you're on top of Everest or, you know, in a trench somewhere. We're just basically saying that that number is relatively unchanging as long as you're on the surface of the Earth. Cool. And so the gravitational equation says that the force of gravity, basically the force that is attracting this mass to the Earth, kind of like a magnetic, kind of like, it's like a magnetic attraction, or just as a visual. It's not magnetic, but just as a visual, it's kind of you have both the Earth and this rope are being, like sucked together. And so a movement of one causes a movement in another. That's not for this video, but that's good to know when it comes to dynamics, is that if this thing moves, that thing moves. This moves, that moves. You jump up, the Earth jumps down. You know what I mean? So that's really bizarre. If you're a basketball player and you're on this Earth over here playing some basketball, and you jump up, you know what I mean, real high, and guess what? You went up that direction, the Earth also went that direction. You know what I mean? So obviously not for this video, but it's just good to kind of know where this stuff comes from. Because if you go all the way to its source, there's nothing farther beyond that, to kind of comprehend. But if you just start using in statics this idea that the weight is just mass times gravity, because you're on Earth, you're just like, where the hell did this come from? Because we know that this gravitational can change, and we know that gravity is a function of the distance away you are from, it's basically the radius of the Earth. It's a function of the radius of the Earth. As long as the mass of the Earth doesn't change and the mass of the rope doesn't change, it literally is a function of the radius, and we're going to see that. So the force of gravity is the gravitational constant times the mass of the rope, mass of the Earth divided by the radius of the Earth squared. And you can see this thing doesn't change, the mass of the rope won't change, gravitational constant, that's a constant. And radius of the Earth, that could change, depending on where you're setting up this experiment. Okay, so these three things add up to G, so that's where you get the mg. Alright, now finally, you know what I mean, and I kind of made a mess of this, where I wanted to go with this, so let's draw it kind of one more time. So we have the rope, and so sure, we have a tension in this rope. We did our free body diagram. We chopped it out of outer space, went back to Earth, saw that we had 15 newtons there, 15 newtons here. Okay, so now what we want to do is what, no one ever taught me, because I just figured I just didn't know how, even though you actually have to do this in statics at some point, and I don't know what you do. I think you just rely on guessing. But what happens is that you can chop this up as much as you want. You know what I mean? And so I would always chop it up from a known end. So we know that we have this rope now floating in outer space, and we're applying 15 Newton force at that end and 15 Newtons here. So if we come in and chop this right here, so now let's draw that. So we draw this, and maybe like kind of do a jagged end right there. But now what we know on this little chunk of rope is that we have a 15 Newton force there, because we don't lose that aspect. So cool. So now we have this little chunk of mass of rope in outer space. You know what I mean? So again, we can just be like, hell yeah, that thing is just in total outer space. We applied a 15 Newton force. We go back to Earth and see that that chunk isn't moving. This chunk that we now want to analyze is stationary. The velocity is 0. And so we go back to outer space, and the only way to get this chunk to have a velocity of 0 is to have a force going in the opposite direction. Now, where do we put that force? And this comes into, you can't apply the force to things that, aren't, like right back here. There's a spring that pulls this rope that way, a spring that pulls this rope that way. Besides the gravity and the normal force up and down, there's nothing else touching this rope. And so, so the only place that you can apply forces, or that forces can be applied, or I don't know if it's applied or visualized, is where you made the cut. So anywhere where you cut, like right there as we made our cut, well, yeah, hell yeah, we can have sky's the limit. You can have a normal force, you can have a shear force, and you could have a moment. And you could have, besides the normal force, you could have a shear force in two other directions. So you could have a shear in the Y, and then a shear in the Z, and then the moments. This could be moments in 3 directions as well. But for two-dimensional stuff, just to get the hang of it, okay, so we chop that rope, we could have a normal force, and we could have a shear force. And so shear forces we'll get into, like if this was a plank of wood. But for this one, this is the simplest. We don't have a shear force, and we don't have any moments. And so this one, we could have just guessed that if I have a 15 Newton force there, the only way to keep that mass stationary is to apply a 15 Newton force on that side. And so that was kind of the whole runaround, just to show you that the tension in a cord or in a rope is always, well, and then let's say I wanted to actually take this chunk in the middle. Well, if I wanted to take that chunk in the middle and find it, I might just be guessing. I might just be guessing that, well, I have a 15 Newton force there at the end and a 15 Newton force there. But if I see that this slice is this end, now I'm in business. Alright, hell yeah. No, this is going to be really good, because I swear, just to say that if I chop this out and I know the reaction right at this slice is 15 Newtons that way, I think it's not intuitive just to say, oh, that there must be an equal and opposite 15 Newtons this way. So let's slow this process down. And what I'm going to do is kind of redraw. Let's redraw this thing. So we have our rope, and we want to, we want to figure out what's happening in the middle. You know what I mean? And so we chopped it out. We got the 15 there and 15 there. So we did that. We were pretty satisfied. Then we chopped this one out, and we said, well, we know that there's 15 on this side, and then, you know, because this thing's not moving, there has to be 15 on that side. But now we want to go right towards, like, hey, what's this? And instead of just saying, oh, it's going to be equal and opposite, so this will have a 15, let's not do that. Let's not do that, and let's keep using we want to know the force right on that side. We want to take an object, and we want to know, and of this, we want to slice this up, and then on this cut right there, we want to know what force is on that, what direction of force and what magnitude. And so to do that, I think the best way to do it is to come in right here. We already took this slice, and so what we're going to do is we're going to take a slice just right next to this slice. You know what I mean? So now I'm going to blow it up just a little bit, but we're going to have now this chunk right here. So we do know that there's a 15 Newton force on that side, and we have this little chunk of rope. And you can imagine this chunk of rope is just just molecules of rope, where like here's the rope, here is the end that we just found. So we chopped that out, and then here's our little molecules. And so we found that there was 15 newtons there. Well, we're going to come in and we're going to just chop along that line of molecules. And so now we just have that little line of molecules, and we got 15 newtons that way. And so there must be a 15 Newton force on that side. Cool. So that's right there. That's what we're going to find. So we're going to see that there's a 15 Newton force going that way. So now, since we know that, alright, so I feel like that was a little bit much, though. You know what I mean? But I like that visual of being like, okay, I can get a line of molecules, know that there's 15 newtons there and 15 newtons there, and just kind of assume now that if I take a cut on this side, I'm still going to have that 15 newtons, and then I can come over here and do 15 newtons. But now, you know, just setting this up, I get how you can get there from a more simplistic way. So let's set it up again, and we'll draw it a little bit bigger. So we have our rope. But I think this is good. I mean, we're spending hella time just on linear tension in a rope, and then kind of dissecting it. So I'm just going to chop this up into 3 pieces. The first free body diagram, hell yeah, we know there's 15 there, 15 there. So now what I did is I came in from this side. Ultimately, we want to know what's in the middle. You know what I mean? But let's do this side first. So we're going to come in. We know that there's 15 newtons on that side. There must be 15 newtons here. Cool. So now what we can do is if I want to get this side, then let's just take the whole slice. Now we're gonna chop out this much. I still have the 15 newtons there, and then I come over here. Whoa, I got 15 newtons. So this literally shows you what's happening at that side. Now I'm going to come over on this side and then chop out that much. I know that I have 15 newtons there, and then I must have to have 15 newtons here, again, because this is not moving in space this way or that way. Cool. So now I know on this cut face I have 15. So now I can come back to chopping it out in the middle, and I can see on this cut face I have 15 newtons, and on that cut face I have 15 newtons. Alright, so hell yeah. So that was a pretty good, I think that was worth it. I think it was worth it going through all that, because I mean, that's at the basic, and it's just kind of fascinating. Like, I've never had it taught to me that way, but I wish I did. So anytime where I'm just like, I wish someone showed me something like this, because then I can use this as a tool to, do more complicated things. Like, that's what I'm always going to do. So anyway, so that was tension in a rope. All right, hell yeah. So now let's kind of get on with this video. And what we're going to do, because we do have this ribbon is a rope. And anywhere where we slice it up, we can know that it has a tension in the rope. And I don't know. That's the other thing is I guess I didn't. Maybe we should do one more picture. And this could be useful. Because what we're going to have in this scenario is like, we're going to have a pulley. So let's say we have a pulley attached to the ceiling. And then we're going to have a rope down. And then we're going to have it attached to a spring to the ground. Cool. And then so this is the rope part. And so if we do a free body diagram of that rope, we're going to chop it out of outer space. We're basically going to just put it into outer space and then go back and forth to Earth and see, what do we know? Well, I do know that these springs, there's a readout on both of these springs, and they're reading 15 newtons. So sweet, I know that there's 15 newtons there and 15 newtons there. And so now, just by, I'm not going to go into all the details, but I mean, you can totally see that if I chop out this piece of rope, so let's do that, chop out that piece, I'm going to have 15 newtons there, and then I must have 15 newtons there. Okay, hell yeah. And I guess it gets complicated. Maybe we should take a look at this. Like, what happens when we chop out all the way up to here? You know what I mean? Because now I'm going to have this chunk of rope. And I'm going to have 15 newtons down. But then over here I'm going to have... Alright, hell yeah. I feel like I'm going to have to prove something. I mean, obviously, a rope has continuous tension. So you are going to have 15 newtons there. And just by what we know about ropes and cables, you're going to have 15 newtons there. But if this was floating in outer space, it would be traveling that way and that way. And so we know that's not the case. And so what we know about this pulley is that we have a constant force kind of in all radial directions from the center of this pulley. And so these arrows help balance this 15 Newton force, and these arrows help balance that 15 Newton force. So we have a net motion of 0, but that's more complicated than I want to get into. But now we're going to do what I wanted to do from the start of this video, is we're going to take this drum, and then we know that this ribbon is wrapped around and it's a rope. And we know right at this junction, we're going to, well, I guess, oh man, I kind of don't know what it's like. Sometimes you don't know what you're cutting. Like, am I cutting the rope itself and then cutting the rope right through there and then cutting the rope right through there? So I have not only the drum, but also the rope that goes around, and I'm cutting the rope right there, cutting the rope right there. So on this, I'm going to have 15 newtons right there, and then 15 newtons right there. And the angles are always really hard for me. So this is a 30-degree angle, and sometimes it's hard to visualize. So what I do with angles is to really like make them kind of on the extreme. So we're just going to make a shallow angle. And then we're going to do this as our circle. And so from here, we are going to go, okay, because this is going to be perpendicular. So here's the center of our circle. This is a perpendicular. So for this to be perpendicular, we're going to have a shallow angle there. And you should get kind of similar triangles. So I didn't leave enough space on the paper, but now I can kind of just do the 30 degrees like it is, come up, and then see that this triangle right there is also 30 degrees. So that's a perpendicular. This is 30. I'm just going to say theta. That's 30. Sometimes I like to do the other triangle. So if this is 30... this is my right triangle there. That means that this is phi. And then this is 30. This is my right triangle. This is phi. So phi is going to be 60 degrees. Theta is going to be 30 degrees. Okay, so now I know, you know, kind of, and I can just do this vertical and say that's my angle 30 degrees. Cool. All right, but we're gonna get even simpler than that. You know what I mean? So now let's draw the drum, and we know that the rope is attached to it, and we know that we have a 15 Newton force this direction, and a 15 Newton force that direction. So let's go back to just the idea that this thing is in outer space, and well, F equals ma. This says that, hey, this thing should be traveling that way, and then actually that way. But then we go back to Earth, and we do our observation of this experiment, and we say, hey, this thing is totally stationary. The velocity of all mass particles on here are 0. Even though this thing can rotate and spin, this is a statics problem where they're just saying, hey, we're just tensioning these rollers, but there is no motion. So that might be something where it's kind of hard to, I don't know, in some of these drawings, they're really hard to get the whole picture. Like, I didn't really understand if this thing was spinning or what. That the fact that these rollers could roll, I mean, I guess just by definition, they're called rollers. I actually had to look this one up just to see that, yes, this is a device where these roll, and it rolls back and forth in this frame. Okay, so, but we know, so we have this mass of the roller, and then we have a force on it. So we are going to see a change in velocity in those directions. But we go back to Earth, and we know we don't see a change in velocity. So we need to have forces that balance these, you know what I mean? So, and this is kind of, besides the equations for statics, setting up the free body diagram, the other most important thing is to identify where there could be other forces. And the places that you're going to have other forces are at your contact points. Because if I look at this circle, like all through here, I'm not going to have any other forces. There's nothing touching this side and that side of this roller. But I do have a contact point there, so hell yeah. So there's going to be a contact point, and I do have a contact point with the ground. So anytime that you have a contact point, and so so here's like a chair leg with a rounded end, and then it's just on the floor. What's going to happen is that you're going to have a normal force that's perpendicular to the direction that this thing is applied to. Another diagram would be like if you had a corner and then you have a wheel, and then you had a, you know, something pushing up against the corner of a corner of a wall. You're going to have the contact point is going to be right there, so you're going to have a normal force right there and then a normal force right there. Now these could be different, so this would be normal force A and normal force B. Cool. All right, so and then at contact points you could have a variety of things. I mean, that's where if you have something that's welded to the ground and you're applying whatever forces up here, cut from the ground, if you cut that out, you could have a normal force, you could have a shear force, and then you could also have a moment. Cool. And yeah, let's do that one, because we're going to have a maybe you do have a weight on here. Yeah, the whole point is to do a bunch of examples where you're just not freaking out about free body diagrams. So, hell yeah, you're going to have this weight. That means that, and you're going to have this force. And those are the two that we identify, but we chop this out of the ground. So we have to make sure, so a couple things. So we take this and, well, we have to balance this force, and we do that with this normal force. That's sum of the forces in the y. So we have a W, a normal force up minus a W, that's equal to 0. That's sum of the forces in this y direction. You do sum of the forces in the x. So now we can totally see that this shear force is that direction. So we have F being positive minus V, that's going to equal 0. And then we have to sum the moments. You can take that at any point, but let's take it right here. and we're going to sum the moments about this point. So we have a length on here, and we have the moment is going to be a negative FL, and then we have to add it to something to have it equal 0. And so the way to do that is, and there's no other forces that are, that's the only force that's generating a moment, so then we just have to add a moment. So that's the moment that we add. If this is generating a negative force, we have to actually generate a positive moment that direction, which we labeled. And so we have negative FL plus that moment, that has to equal 0. So this moment in this case has to equal FL. So those are the 3 reactions that are going to happen at a welded joint where it's a rigid joint. Cool. Now, when it comes to this chair, we know that maybe, yeah, like, I mean, obviously the chair will probably have another leg that way on the other side. And so you could have this chair on ice. You know what I mean? If this chair's on ice, you could still sit on it. It's got normal forces, but it's not sliding across. But you can have things where, you know what I mean? If this is like a, I don't know, just like a wooden stick, and you're leaning up against it, but it's not sliding across the ground, well, that must mean that there's a frictional force, you know, this way. So those are going to be your forces. So you have a normal force, your frictional force could be like your shear force, and those are the forces on the ground. Or, I mean, I should just say, you should do the free body diagram. You should chop it out of outer space. So we're going to take that chair leg, or like a wooden stick. So this would be like a wooden stick that you're leaning against. You know what I mean? You're kind of just doing some work, but just leaning against a stick on the ground. But it's not moving. You're putting your body weight against it. It's not moving. So we cut the stick out of outer space, and then we know that there is a force downwards. So we have a normal force, but then we also have a shear force up against the stick, and this shear force would be your friction force. Those are the 2 forces that you can have. And I don't think in this case you would call it a shear force. They would just call it the friction of the ground. Cool. All right. So now we have. So now we've identified that this mass isn't moving that way or this way. So now we know that we have to counteract it. We have to counteract these 2 forces that would cause this thing to go this way and then this and like in a direction that way. And so, and we're going to say that this is a frictionless surface, because a lot of these problems, you know, they kind of just make everything frictionless. Just imagine it's just made out of ice. And so we're just going to have a normal force here. This contact point is just going to be a normal force. It's going to be like a chair on ice. We're not going to have the friction force. So that's kind of what they're getting at right there. Now this can balance that one, but this thing is still going to travel that way. So what other places do we identify at a contact point? We're going to have a contact point there, and that's going to be normal, is perpendicular. So draw a perpendicular line between those surfaces. Just like if this was a chair leg and the ground, there's the perpendicular line between that kind of rounded surface of the chair leg. Okay, so right here is going to be, you know, we're going to have a force in that direction. And you can totally see what we need is a force in, you know, we have both of these going in this direction, a component of, so we need something going in that direction, and this would do it. So this would be the normal force. It has a component in that direction, and now we're kind of good. And a lot of these are going to duplicate each other, but this is the only one that actually has a component in that direction that can balance those two. This force has a downward component and a component in, let's say, the positive x direction. And so this portion of that force is the only thing that can balance this and that. So now you can see that this normal force right here is going to be quite high. And I'm just saying, like all these are normal forces. You would want to label them different things so you're not mixing up this end for that end. All right, hell yeah. So, I mean, and then just with vectors, how they work is like, you know what I mean? You could basically say this is 15 that way, and because this is like 30 degrees, well, I don't know. Actually, this is probably a steeper. What did we say? If we had, yeah, this is going to be a steeper angle. So this is mainly down. There's only half of this in that direction. So we're going to have 15 plus 7.5. That's going to be 22.5 newtons that way. So this component right there has to be 22.5 newtons. That means that the actual, the hypotenuse, or the actual vector that can generate a component that has 20.5, and the angle on that's going to be 30 as well. And so you're going to take 22.5 divided by cosine 30. And so this force right there is going to be 25. That's that 26 newtons. So the normal force up against these two are going to be 26 newtons. So that's kind of cool because that's exact. So the normal force in between these two are going to be the same normal force that's being applied to the ceiling. So that's actually pretty cool. We actually learned something from this problem. Is we chopped up just this mass. We identified that we had a 15 Newton force that direction. We have a tension 15 newtons, but only half of it's going to be applied in that direction. And so we have 22.5 newtons that we have to. That's basically like taking this mass, putting a 22.5 newtons on it in that direction, and using that same principle. Like, hey, this thing's in outer space. We need a force going the other direction. Now, it can be anywhere on here because we're not worried about this thing rotating yet. We just need something to balance it. So, like here, we could apply a 22.5 Newton force in that direction. And what we see is that we're applying it right at that contact point. And we're just applying, and only this component of it has to be 22.5. We have an angle, how does this work? Did I do this right? Because we would have a 30 degree angle here. I feel like I didn't do this right. No, that's right, because this is the cosine component. If this is like the vector that I'm wanting, this is the bigger number, the hypotenuse. I want to know the hypotenuse, and I know one of its legs. This side is 22.5. I do know that this angle is 30, so I know something about the cosine component. The cosine of 30 is the adjacent. This is the adjacent part of that triangle. So if this is the angle, sun is shining. This is the sine component, this is the cosine component. So I can see that cosine 30 is 22.5 divided by the hypotenuse. So I can just rearrange this equation, and then the hypotenuse, that larger number, is 22.5 divided by cosine 30. But yeah, maybe I'll make another video on that, because I think there's two things that are very useful. Is to, if you know the hypotenuse, how to find the adjacent components. You know, if you know the hypotenuse and the angle, well, this is the sine component of the hypotenuse. And sine 30 is a percentage of the hypotenuse in this vertical direction, or the opposite direction. And this is going to be cosine 30. And cosine 30 is a percentage of the hypotenuse. And this percentage is always between 0 and 100%. It's a fraction between 0 and 1. But if I know the smaller number, like if I know this side and I need to know the larger number, the hypotenuse, I know it's related to the adjacent or cosine component, so I take that 22.5. Oh man, can you see this? So I take that 22.5 and then I divide it by a smaller number. See how 22.5 divided by a smaller number between 0 to 1 is going to generate, that's going to generate that larger number, that hypotenuse number. So that's just one to, like, I don't know, it's okay to, you know, just write out the equation and then rearrange. But I think that's a good one. That was a good one for me to throw in my wheelhouse to get there by memory. So again, this 15 adds with half of this 15. And we get 22.5. That's this component. What's the hypotenuse? That's going to be 22.5 divided by the cosine of 30. And so that's 22.5 divided by 0.8866. And hell yeah, and that's going to be a larger number. That gets us up to that 26 newtons. And just for this problem, it's kind of cool is that the normal force in between these two rollers is the same normal force on the ceiling. And yeah, so let's finish the video with that to be like, okay, so let's do this top roller and let's see if that jives. So we're going to come in here. We have this is our 30-degree angle. We're going to, and we know we have a normal, what do we have? We have 15 newtons there, and on this one we're going to have 15 newtons this direction, so we're going to have 7.5 in that direction, and then, cool. And then we're going to have a normal force this way. Yeah, this normal force was going this way because these two forces were causing this mass to travel this way and that way. So we had to balance it with that. This is a mass. We see this 15 newtons there and 15 newtons there is causing it to go this way and that way. We need to prevent that. We need to have some sort of forces this direction. This is the contact point to do this. This contact point actually doesn't do anything. But we're just going to throw the 26 newtons in on all of these and then just make sure that we have a check on reality. So we're going to sum the forces, and we need our angles in here. So this is going to be 30. On this one, this is going to be our 30 degrees. Cool. So we're going to sum the forces in the x direction. That's going to be 0. So we're going to have this one. If this is the angle, sun is shining. This is the sine component. This is the cosine component. If this is the hypotenuse, it's the larger number. We need to take that 26 newtons and then multiply it by a smaller number, that fraction. That's the cosine. Cosine of 30. And so we have 26 cosine 30, and that's going to be in the positive x direction. And this one is going to be negative. So we have negative 15, and this is the sine. You know, draw your angle, draw some sunshine and rays, and that's going to be the sine component. So 15 sine of 30. Sine of 30 is 0.5. So this is going to be that 7.5. This is going to be that 22.5. 26 cosine 30. And this is going to be a negative, so we have a positive 22.5 minus 7.5. We're going to have minus 15, and we're done. So cool. So we have 22.5 minus 7.5, and that minus 15. Cool. So that's 0. So we do have a check on reality there. We're going to sum the forces in the y direction are 0. So we have this component. So we're going to take that 26. Sun is shining, sinin. So we have 26 sine 30. That's positive. This one is going to be 15 cosine 30 plus 15 cosine 30. Because the hypotenuse is 15, but we want to know this adjacent part. If here's the angle, the sun is shining on the sinin, the cosine component is the adjacent part. So 15 cosine 30. Okay, hell yeah, and we want the vertical direction, and now we're going to do minus 26. So sweet, so we have 26 cosine 30, that's that 22.5. We have 15 cosine 30, that's going to be plus 12, basically 13. And now we're going to, oh, is this one going to work out? I feel like I messed up. Yeah, this normal force. Yeah, let's just try it out, I guess. So 26 sine 30. Yep, I'm satisfied with that. Plus 15 cosine 30. Alright, sorry about that. My camera ran out of juice. So, yeah, so I did make a hiccup. I said this was going to be 22.5. No, so this is a shallow angle. It's 30. We want the vertical component. This is 30, so we want the sine component. So the sine component of this 0.5. So you can see that if this hypotenuse is 26, this component's only going to be half of that. So we have 13 newtons there. So in the vertical direction, this is going to be 13. And then this component is at a 30-degree angle. It's 15. And we want the cosine component, which is very close to 15, but it's going to be 0.866 times 15. That's 86.6% of 15. That's going to be 13. So we have 13 plus another 13 newtons, and then subtract 26. So we have 13 plus 13 minus 26, and that's 0. So we do have a check on reality there. All right, sweet. All right, hell yeah. So I think I'm done with this one. Thanks for joining me. And yeah, I'll try to make some more free body diagrams because it fascinates me. It fascinates me that you can literally chop anything out of this and kind of get an answer, you know, and make it make sense. So that's pretty cool. Yeah, so let's end on a kind of a more technical note. So if I'm saying that this normal force is 26 newtons and this tension is 15 newtons, and I can chop out anything of this, and so what I'm going to do is I'm going to come in here and kind of chop out that little chunk. So let's blow it up. And so if I chop out this little chunk, we exposed a surface, and I said if we exposed a surface, we can get a normal force, we can get a shear force, and then we can get a moment. And it really doesn't matter, you know, what direction you put these in, and then put the actual, and then we're going to say this is going to be 26 newtons that way, and then we have 15 newtons that way. Okay, so now you can just see visually, if this is a chunk of mass, you know, floating in outer space, and we put 15 newtons this way, well, we must have to, you know, put a force of 15 newtons that way. The only place that we can do that is on the cut surface. So we just did that. Now it's balanced this way. This is a 26 Newton force upward. So this little chunk would have been traveling that way. But we go back to our problem and see that none of these mass particles are moving at all. All their velocities are 0. So we have to have something that balances this 26. That normal force does it. So we're going to have a 26 newtons downward. Sweet. And then what we see is that, hey, let's say this, yeah, no, I got to be careful about this. No, it's like for sure. And we're just going to say this is the ground at point 0. And, you know, let's say we just went up 5 millimeters. So this distance is 5 millimeters. What we see is that, and maybe we should almost draw this again, but we see that this thing is going to spin. So so we have this little chunk. We have 26 that direction. We got 26 that direction. So we're chill there. But on this surface, we have 15 newtons that direction and 15 newtons that direction. This is going to cause it to rotate. That's going to be a positive. So we have a positive moment going on. And but from observation, this thing's not moving. So we must have to have other forces that cause a negative moment. And we don't have any other places to put forces, but we know that this surface is technically a welded surface. You have bonded chunks. Let's say the rollers are made out of metal. That, you know, they're all, you slice that apart. Yes, you expose a surface that you can have a torque on. And so these are going to generate a positive torque. So we're generating this amount of torque. And we said that this is going to be 5 millimeters. So this 15 generates 15 times 5. Oh man, it's hard for me to do math. That's 75. That's a 70. So this torque generates a positive 75 Newton millimeter torque. And so we have to couple that with a negative 75 Newton millimeter torque. So that is the torque in the opposite direction that makes this chunk not, you know, so now this chunk's not flying through space this way, and it's not rotating. So so that's pretty cool. And so that's kind of what I want to do more of. And it's just fascinating. It's just like, I don't think, if a problem said, hey, you know, let's cut through that little chunk right there, would you be able to figure it out? In material mechanics, that's what you do all the time. And you know, and then you don't even take your chunk, like you don't cut through at a nice angle like that. You might take the chunk and then cut through like at a 45. You know, so now you have this going on, and you know, all the same principles apply. You're going to have a shear force, you're going to have a normal force, and then it has to balance with this 26. It has to balance with this 15. So hey, this component. This has a component that way, and this has a component that way that can balance this 15. And this upward component can only be balanced by this downward component. But who's to say that this shear force couldn't be in this direction? But let's see if that would even make sense. If we have because this 26 could be balanced by the downward component of this. This 15 could be balanced by the over component of that. But yeah, so now you kind of have this nice balanced ratio where who knows what direction this goes in. There's probably a slice where you're not going to generate any shear force at all. So that's kind of an interesting thing. But anyway, so I think I'm done with this. That was probably the more advanced thing. But that's what I want. You should be able to chop it up any way you want, make it make sense, and make your head not explode. So anyway, thanks for joining me. And guess what? That's a video.